Hi friends, welcome to my channel. Now, ionic solids comes under sodium chloride, lithium fluoride, MgO, MgCl2, KOH, and Al2O3, whereas covalent solids comes as silicon, germanium, carbon, lead, and tin. Now, if you consider as metallic bonds, sodium, copper, gold, silver, aluminum, whereas cubic lattice parameters A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, number of space lattices equal to 3. So among that simple cubic, body center cubic, face center cubic, okay na, KCl, Cu, ZnS, CuTO, CsCl, CaF2, alpha Fe, beta Fe, gamma Fe, aluminum. The rhombohedral lattice parameters A equal to B equal to C, alpha equal to beta equal to gamma, which is not equal to 90 degrees, number of space lattice equal to 1, substructure in simple rhombohedral. Examples are CsCO3, Al2O3, SB, Tetragonal A equal to B is not equal to C, alpha equal to beta equal to gamma equal to 90 degrees, number of space lattices equal to 2. That is simple tetragonal, body tetragonal, SnO2, TiO2, radium, arsenate, iron comes under tetragonal. Whereas if you consider as orthorhombic lattice parameters, A is not equal to B is not equal to C, alpha equal to beta equal to gamma equal to 90 degrees, number of space lattices equal to 4. Simple orthogonal, body centered orthogonal, face centered orthogonal, base centered orthogonal. The materials are K2SO4, BaSO4, MgSiO3, KNO3, S. Now if you consider hexagonal lattice parameters, A equal to B is not equal to C, alpha equal to beta equal to 90 degrees, whereas gamma equal to 120 degrees, number of space lattices equal to 1. Simple hexagonal ZnO, Mg, Zn, cadmium, Cd. Now if you consider monolithic means A equal to not equal to B is not equal to C, whereas alpha equal to beta equal to 90 degrees, gamma is not equal to 90 degrees. CaSO4, gypsum, plutonium comes under monoclinic. Triclinic, A is not equal to B is not equal to C, but alpha is not equal to beta is not equal to gamma is not equal to 90 degrees, number of space lattice equal to 1. Simple triclinic, CuSO4, K2Cr2O7. Atomic packing factor, total volume of atoms in a unit cell by volume of unit cell. Suppose APF equal to n atom into V atom by V unit cell. N equal to number of atoms in a unit cell, V atom equal to volume of an atom, V unit cell equal to volume of unit cell. Crystal structure in metals. First one is simple cubic structure. Simple cubic structure. A simple cubic structure, atoms are arranged at the corners of the cube. Unit cell of simple cubic structure has 8 corners and all the corner atoms touch each other. Example, polonium, manganese. Effective number of atoms n. Each corner atoms of SC structure is shared by 8 unit cells. Thus, each unit cell shares 1 by 8 of the corner atom. There are 8 corners in SC structure. N equal to 8 into 1 by 8 equal to 1 atom. Relation between lattice constant and radius of atoms. A equal to 2R. Atomic packing factor equal to volume of units, volume of atoms in the unit cell by volume of unit cell. A equal to 2R, R equal to A by 2. Volume of atoms in the unit cell equal to 1 into 4 by 3 R square. 1 into 4 by 3 is not equal to R cube, equal to 4 by 3 is not equal to A by 2 whole cube. Volume of unit cell equal to A cube. APF equal to volume of atoms in the unit cell by volume of the unit cell. APF equal to 4 by 3 pi into A by 2 whole cube by A cube, that equals 0.52. Empty space in simple cubic structure equal to 1 minus APF, 1 minus 0.52, that equal to 0.48. Coordination number for simple cubic structure equal to 6. For metals, each atom has the same number of nearest neighboring or touching atoms called as coordination number. Body centered cubic structure. In this structure, the 8 corners of the cube are occupied by 8 atoms, and the center of the cube is occupied by 1 atom. Chromium, tungsten, alpha iron, vanadium, sodium. Effective number of atoms in the unit cell of BCC structure equal to 8 into 1 by 8 plus 1 equal to 2 atom. Relationship between lattice constants and radius of atoms. Consider a cubic diagonal. 4R equal to A root 3, R equal to A root 3 by 4. Atomic packing factor equal to 2 into into 4 by 3 into pi r cube by a cube that equal to 0.68. Empty space in a body centered cubic unit cell equal to 0.32. Coordination number of BCC is 8. Face-centered cubic structure. In this structure, the 8 corners of the cube are occupied by the 8 atoms and 1 atom occupied at the center of each of 6 faces of the cube. Examples: nickel, aluminium, copper, silver, gold, platinum, lead, iron are the noble metals. Effective number of atoms in the unit cell of FCC structure equal to 1 by 8 into 8 plus 6 into 1 by 2, that equal to 4 atoms. Relation between lattice constant and radius of atoms. Consider a plane diagonal. 4r equal to a root 2, a equal to 4r by root 2. Atomic packing factor 4 into 4 by 3 pi r cube by a cube, that equal to 0.74. Empty space in the FCC unit cell equal to 0.26. Coordination number for FCC is 12. Hexagonal closed packet structure HCP. The structure contains one atom at each corner of the hexagonal. Like that, hexagonal structure is having 12 corners, one atom at the center of the two hexagonal faces, bottom and top. Three atoms in the a form of a triangle midway between basal planes: zinc, cadmium, beryllium, magnesium, titanium, zirconium, etc. Effective number of atoms in the unit cell of HCP structures equal to 12 into 1 by 6 equal to 2 atoms at corners, 2 into 1 by 2 equal to 1 atom at basal planes, 3 atoms inside unit cell. Total number of atoms equal 6. APF equal 0.74. Empty space in HCP unit cell equal 0.26. Coordination number for HCP is 12. Diamond cubic structure. The diamond cubic structure consists of FCC structure with 4 atoms are arranged inside the unit cell with cubic diagonals at 1/4 distance from corner. Diamond, germanium, silicon. There are 18 atoms in unit cell, of which 8 atoms at corners of the cube, 6 atoms at the centers of 6 faces of the cube, 4 atoms are inside the cube. The effective number of atoms in the unit cell is 8. Relation between lattice constant and radius of atoms: 8r equal to 8 root 3. 8r equal to a root 3. Atomic packing factor equal 0.34. Thus, the packing is least in the diamond cubic structure. The strength of a solid depends upon the type of bonding and not on packing. Suppose A4 BCC 4r equal to root 3a, FCC 4r equal to root 2a, DCS 8r equal to root 3a, HCS D 3 and A equal to R. Theoretical density of unit cell equal to P equal to Na by VC Na. N equal to number of atoms associated with each unit cell. A equal to atomic weight. VC equal to volume at the unit cell. Na equal to Avogadro's number. 6.023 in 10 power 23 atoms per mole. Crystallographic planes. Crystallographic planes are specified by Miller indices as HKL. Miller indices are obtained from lattice parameters ABC. Single plane representation ABC. Family of plane representation ABC. To represent the different planes and directions in any crystal structure, a 3-digit index system is used. Procedure step 1. The intercept lattice parameters are ABC. Take the reciprocal of their intercepts 1 by A, 1 by B, 1 by C. Reduce these intercepts into the ratio of least integrals of HKL. Enclose them in parentheses. Use you H. Interplanar distance to the distance between a set of parallel planes. HKL, that means DHKL equal to 1 by root over H by A whole square plus K by B whole square plus L by C whole square. Linear density equal to number of atoms centered on direction vector by length of direction vector. Planar density equal to number of atoms centered on plane by area of the plane. Thank you.